problem, shall we? I think I'll take off my reading glasses. I have Ryan here helping me out. Hey, Ryan. Hi. Okay, so let's find the inverse, which I'm calling g of x, of f of x equals the square root of x squared plus 9, with the domain restricted to x greater than or equal to 0, and calculate g prime of x two different ways. All right. Let's just try it the good old-fashioned way. Let's just find g of x and take its derivative. Shall we do that? All right, so if this is f of x, of course, I can replace that f of x with a y. And as we know, an inverse function undoes what a function does. In other words, the x becomes the y and the y becomes the x. So the function g is going to be x equals the square root of y squared plus 9. All right. Now, you don't have to solve for y. I could just do implicit differentiation. But I probably could solve for y. So let's just solve for y, just for good old, for something. Let's just solve for y. All right. I think I can solve for y by squaring both sides and then subtracting 9. You're just peeling off the layers like an onion. And then I can take the square root of both sides. Now, just always a good habit whenever you take the square root of a variable that's squared to think plus or minus, but of course this domain was restricted. So if that x is going to be a positive, it's going to be greater than 0, then I'm going to use the positive root. And actually, let's think about this. What would the domain of this inverse be? If the domain of f of x is greater than or equal to 0, I think the domain of the g of x is going to be x is greater than or equal to 3. Which of course is the range of that function, if you think about it. Remember, the domain and the range undo each other. Okay, we didn't really have to write that down, I don't think, but that's handy to keep in mind. Okay, so now I have, this is my g of x. Since I solved for y, I can just go ahead and say g of x. All right, we're looking for the derivative, so let's bring that up here and take the derivative. Of course, I'm going to just rewrite this as x squared minus 9 to the 1/2. So I can do my chain rule nicely. 1/2 x squared minus 9 to the negative 1/2 chain rule times the derivative of x squared minus 9, which is 2x. And I'll just make this pretty. Let's see, 1/2 times 2 is 1 last time I checked. That x is in the numerator. You don't have to write this with a positive exponent, but I'm just going to for fun. There's my derivative. Now, it might be fun now just to pause the video and sketch these, and you can use your graphing calculator if you want to. Of course, a function and its inverse will always be a reflection over the line y equals x. So this is kind of an interesting function and its inverse. So go ahead and see if the graphs of these seem to work, because those are kind of fun. All right, we just found the derivative one way, just by finding the inverse function and taking the derivative with respect to x. But let's try it using the cool theorem that gives us the relationship between a function and the derivative of its inverse. Shall we do that? So recall that if f and g are inverses, then the derivative of g is 1 over f prime of g of x. Of course, the f's and the g's are interchangeable here, right? If g is the inverse of f, f is the inverse of g, etc. Okay? I'm going to tell you right now that this way is a little more contrived. I think the first way is a better way to do it, but let's just see that it works, just to satisfy ourselves. All right, so I need the derivative of f prime. So let's go ahead and find the derivative of f prime. F prime is, the derivative of f prime is 1/2 x squared plus 9 to the negative 1/2 times 2x. Chain rule. Which simplifies to x over x squared plus 9 to the 1/2. Wow, that's funny, isn't that? Okay, so that's our derivative. So if I want to find g prime of x, let's bring it over here. G prime of x is going to be 1 over f prime, and I'm not going to fill in the x's there. And maybe I'll do the square root, that's okay. The reason I'm filling those, leaving those, is because that's going to be my g of x in there. Okay, a couple things are going on. One is I have a complex fraction. If I have 1 divided by this crazy fraction, can't I just flip the whole thing? Isn't this just going to be, let's see, the square root of g of x squared plus 9 all over g of x? Yeah, I think so. I think we're good there. Okay, so if that's the case, all I have left to do is to substitute g of x in. Well, what is g of x? I guess I have to find g of x. And I find g of x the way I found g of x before, finding the inverse of f of x. So the y becomes the x, and the x becomes the y. And I solve for my y, which I already did just moments ago. So I'm just going to, whoops-a-daisy. So square both sides, subtract 9, take the square root. Okay, so that's my g. So now I'm going to put that g of x into that square root. Goodness, this is crazy. Square root of x minus 9 squared plus 9 all over square root of x squared minus 9. Drum roll, please. We're getting there. Square root squared, well, those undo each other. X squared minus 9 plus 9, that's just x squared. Square root of x squared is plus or minus x, but I have my restriction, so that's going to be x over the square root of x squared minus 9. And ladies and gentlemen, that's what we got using the much easier process of just finding the inverse and taking the derivative. But it was kind of cool to see that that little trick worked. Okay? So you might be saying, well, why in the heck that wasn't helpful at all? Well, this theorem wasn't particularly helpful in this problem, but it is helpful in lots of other problems where it's hard to find that inverse of a function or the derivative of the inverse. All right? And later when we're working with discrete data, like if you just have values and you don't have very much information about the function itself, this is critical also. All righty. That was fun. I hope you thought it was fun too.